Hey everybody, my name is Max Talene, and I'm here to talk today about my mega favorite number. Since this is the first math video I think I've ever posted, first a little bit about myself. I'm a film professor by trade, film scholar, but I've loved recreational mathematics basically my whole life. I got a few sequences on the OEIS last year. The one and only Neil Sloan actually included one of them in a lecture that he gave. I sometimes make experimental film. Every once in a while, I will apply some sort of algorithm to help me make it. And in my professional publishing on film scholarship, I've even done statistical analysis of trends in the history of the IMDb Top 250 to think about changes in mass ideology. So anyway, I love math, and I feel like it's a real privilege for me to be able to try to squeeze my way onto one of these mega favorite number playlists, because I don't usually get to talk about math. So my mega favorite number is this 44-digit behemoth that starts with 101 and then has a whole bunch of digits after that. I originally encountered this number in the Penguin Dictionary. I almost said encyclopedia. Penguin Dictionary of Curious and Interesting Numbers by David Wells. It is toward the back because these are in order by size. It's toward the back, right up here at the top. He writes of it the unique number, which, when the last digit 9 is moved to the front, is the number multiplied by 9. So let me say that again. He says it's the unique number that when the last digit 9 is moved to the front, it's the number multiplied by 9. Now, for me, that's actually one of the least interesting things about it. For some reason, I was reading through this years ago, and it got me started on a journey with this number that I really enjoyed. So the first thing I thought when I encountered this was, wow, how in the world did they discover this 44-digit number as the smallest, and indeed it says unique number, where if you multiply it by 9, the answer you get is that same string of digits, but with the 9 moved to the front. I thought this is absolutely remarkable. How did they ever find this number? And then I realized, actually, it's a pretty easy number to derive. So what we know is that there's going to be some long string of digits, and it's going to end in 9. We're going to multiply that long string of digits that ends in 9 by 9, and the result is going to be 9 followed by that long string of digits. So we know that the first thing that we have to do in the ones place when we start multiplying is multiply 9 by 9. We know what that ends in. That ends in a 1. Carry the 8. And since we know, therefore, that long string of digits has to end in a 1, then we know that the original number that ends in 9, in its tens place, there will be a 1. So we can multiply that by 9. 1 times 9 plus the carried 8, that's 17. So we know that the second to last digit of that long string of digits is going to be a 7. We can move that up to the next line, and we just keep going until this eventually terminates, until eventually we find the end of this number. And it turns out that it takes a total of 44 digits for this thing to terminate, which I thought was kind of interesting, that this is the smallest number that does this. But the book also says that it's the unique number that does this, and I found out pretty quickly thereafter that no, in fact, if we were to double the number of digits, if we were to write this 44-digit string twice, that will have the exact same property. And then I thought, well, wait, what about if the number ended in 8 and you multiplied it by 8 using the exact same method of deriving the number that ends in 9? Could we derive a number that ends in 8? And of course we can. Here's the number you get. And there is also a number that ends in 7 that you can multiply by 7 with this property, and 6 and 5. And if you look closely at this number for 5, you can see that it seems to be, well, it starts with 10, 20, 40, 8, 16, 32, 65. It seems to be some sort of staggered sum of powers of 2, which is weird, interesting. And the same thing can be said of 4, which is, by the way, a pretty short number, as you see there, just 100,564 multiplied by 4 equals 410,256. You can do the same thing with 3 and 2, and if you look at 2, it seems to be a staggered sum of powers of 5. You see 1 and then 5 and then 26, but maybe that's 25 with 125 added to it, and so on. Anyway, there seem to be some patterns inside these numbers that made me want to go back and look at the original string itself. And so I did. I went back and looked at the original string, and maybe you already noticed this, but it seems to be, save for the first 2 digits, it seems to be the Fibonacci sequence. You can see it right there. It starts with 1, 0, but then after that, 1, 1, 2, 3, 5, 9. We would expect to see an 8 there. And then 13 and so on. But again, maybe this is some sort of a staggered sum. And so I rounded up the first 70 or so values in the Fibonacci sequence and arranged them such that their ones place is staggered in the way that you see here, and computed the sum of that. And indeed, what you find is that not only does it add up to this 44-digit number, but I suspect that if we kept adding the rest of the Fibonacci sequence out to infinity, that we would get this 44-digit number with this odd 9 multiplication property over and over and over again, that it becomes a kind of repeating decimal, that it's a number that has a period to it, which is pretty interesting. And it makes me think that maybe when we think about how the Fibonacci sequence begins, some people say that it starts with 1, 1. Other people say that, no, we should start it with 0, 1. On the basis of the existence of this number, I'm going to suggest that maybe we should start the Fibonacci sequence with 1, 0, because that's how this number begins. Another thing I notice, and perhaps this goes without saying, is that you can do this in other bases as well. So in base 4, the number that ends in 3, that when multiplied by 3 equals that same string of numbers, but with the 3 moved to the front, is a pretty simple number, 1, 0, 1, 1, 3. And you'll notice that, again, it starts with the digits of the Fibonacci sequence, plus 1 and 0. In base 5, it's 10, 11, 24, 214. In base 6, it's somewhat longer. In base 7, it's even longer. Base 8's a bit shorter. Base 9 is even longer. Base 10 we've already done. Base 11 is incredibly long, very long string of digits. Base 12, here's what that one looks like, and so on. Feel free to derive the other ones yourself if you'd like. But it would appear that each one of these is also a staggered sum of the Fibonacci sequence in those different bases, which is also interesting to me. The whole thing seems to come down to Fibonacci, but it also has this strange multiplication property. And to be honest, I have no idea why. I don't know why the periods are of the length they are, because, again, in base 3, the period of this number is 4. In base 11, it's 108 digits. In base 10, as we saw, it's this 44-digit number, which is the topic of this Mega Favorite Number video. So there's probably a lot more that we could explore with this number that I don't know. Who knows? I probably even got some facts wrong in this video. I just wanted to be part of this whole Mega Favorite Number thing, and so here it is one more time. My Mega Favorite Number. There were just 2 lines on it in this... Oops. There were just 2 lines on it in this Penguin Dictionary of Curious and Interesting Numbers, but all I had to do was scratch that itch just a little bit, and it revealed a whole bunch more in other bases with other terminating digits as an infinite sum of staggered values from the Fibonacci sequence in any base seems to have this property. It's an interesting number. Anyway, it's my Mega Favorite Number. Thanks for watching.